Mohammed Alahmadi, and I am PhD student at Newcastle University. Today I would like to present my paper, which is about detecting sync flood attack using communication structure, a cyclic net. These are the outline I will go through. In the beginning, I will give a brief about the formal model I used in this paper, which is a cyclic net and communication structure, a cyclic net. Then I will give some introduction about transmission control protocol, TCP protocol, and three-way handshake mechanism, and how attackers use this weakness to overflow the TCP queue of the server and make its resource consumed and unavailable for request of normal user. In the end, I will show you the proposed solution in both structure and behavior or semantic to detect such kind of attack by using colored communication structure, a cyclic net. A cyclic net is a formal model used to analyze and visualize complex evolving system in order to understand the behavior of systems and the causality between events could happen in the complex system. It provides a full and unambiguous or clear record of all causal dependency during in communication or during in the process. This figure shows an example of a cyclic net which can exhibit both forward and backward deterministic. It includes a set of places which indicate system status represented as a circle. For example, here B1, B2 until B4. And transitions represented as a square indicate the transition from one state to another, and the flow relation connect these place to together with the transition. Marking is shown by placing token within the circle, inside the circle, represent the global state now for the system within initial marking. Start with initial marking, B1 in this case. Communication structure, a cyclic net, SYN, are an extension of a cyclic net that have the ability to model behaviors of subsystem using a cyclic net and interaction between subsystem using synchronized and asynchronized communication. It's a set of a cyclic nets to represent the interaction among separate subsystem or different subsystem communicate with each other. Each component of this acyclic net represent a local view of systems behavior. The figure here shows CSA-N, which composed of two acyclic net with synchronized and asynchronized communication. For example, event E and C are two transitions involved in asynchronized communication, as E can be executed before C, or they can be executed together. However, C cannot be or can never be executed before E. On the other hand, due to the synchronous communication between D and F, they are always executed together. So buffer places are extra node responsible to pass token between different cyclic net or between different subsystem communicate with each other. As a cyclic net, the initial marking here is a union of the initial marking for all cyclic net. For example, here the initial markings union of B1 and B5. Transmission control protocol, TCP protocol, is a protocol used to allow exchanging data between different devices by transferring packets over the internet and ensuring the reliable delivery of these packets. Generally, the three-way handshake mechanism allows both sender and receiver to synchronize and acknowledge each other. So it consists of three consecutive steps, as you see here in the figure. First, the client sent a sync message to the receiver or server, in this case, requesting the connect. Second, the receiver respond with both sync and ACK. The sync in this case means that the server is ready to connect and the acknowledgement confirm receiving the sender's previous sync message. Finally, the client send acknowledgement to the server confirming receiving its previous message, and the connection now is established. This is a three-way handshake used in each communication between client and server using TCP protocol. Distributed denial of servers, DDoS attack, is disrupted regular internet traffic by overwhelming servers with a fast amount of data, leading to resource depletion. A TCP sync flood attack is a subtype of DDoS attack, which capitalize on the TCP handshake process to overwhelm the target server and make it unavailable for normal user. So attackers can exploit this by continuously sending sync packet with fake IP address, leading to network saturation and server unresponsiveness. However, more specifically, with such kind of this DDoS attack, sync flood attack involves sending repeated sync request packet to the server port using fake IPs. These requests appear to normal and the server tries to respond to this request by respond to each client send sync ACK and waiting acknowledgement from client, which in turn waste its resource. So attackers use three-way handshake to attack server through three ways. The first way is direct sync flood attack, and second sync spoofed attack, and sync DDoS attack. In the first one, in direct sync flood attack, attackers send a massive amount of sync message from the same source IP address, while in the spoofed sync flood attack, it involves sending a massive amount of sync message from different spoofed IP addresses. However, in DDoS sync attack, which is the most dangerous attack, the victim or servers receive sync packet in the same time from several infected computers under the control of attackers. This combination of attack called botnet. Before going to the analyzing this kind of attack, the motivations for this war are there is a lack of visualization tool that can simulate this kind of attack. So improving the understanding of the behavior of such attack can assist in analyzing the causality of attack behavior. This could lead to help investigator, network investigator, to detect abnormal behavior that may occur or happen during communication between client and server. So this paper focus on enhancing the interpretability of such attack by utilizing the capabilities of CSYN or communication structure cyclic net through formal structures and strong mathematical semantic embedded in their formalization to detect this kind of attack. Colored communication structure cyclic net are a new extension of communication cyclic net, which can now model different token with different values, distinguished by different color. So now CSA-Net can model communication between clients, more than one client and one server. Specifically, it can simulate large number of communication between clients and servers, such that sync and ACK and sync ACK acknowledgement. So we will depend on the semantic of CSA-Net features embedded in their formalization to model and analyze these behavior. These features can help in analyzing and visualizing such communication in order to help investigator to detect abnormal activity during the communication. Now we will go through analyzing and visualizing three-way handshake in both, first in structure and then in the behavior or the semantic of this communication. The CSA-Net, as we said, is a visualization framework, is designed to assist, analyze cybercrime investigation. So we use a cyclic net to represent different subsystems. In our case here, clients and server by individual subsystem and connected them through buffer place. So structurally here, as you can see in the figure, the three-way handshake process can represented by two different acyclic net linked by three buffer place. So this figure demonstrates how client and server communicate with each other by in TCP protocol. The upper one, which is a client, and the server in the lower one, using colored communication structure acyclic net. The places here, C1, C2 until S4, showing by circle, it's showing the current states of the process, for example, sync ACK, or acknowledgement, while transition represented by square here are responsible for transferring token from one place to another place. However, moreover, buffer places here, Q1, Q2, and Q3, represented by bold circle, are responsible for transferring token or buckets between different acyclic net in both synchronized and asynchronous communication. Each bucket or client here in this way represented by token with the features include value, which include IP source, IP destination, port source, port destination, TCP flag, and time value. We will show you how to add this to our model. So in the first handshake, token A, for example, here, and B reside at C1. For example, token A or client A will consume the send sync events. In other words, the client send sync token to the server. So transferring token to C2 and Q1. So now the server is ready to receive sync request from client. As you can see, now receive sync is enabled here in orange in simulation way. So now client send first sync to the server. In the second handshake, the server's receive sync action is activated, transferring token A from S1 to S2, as shown here in this figure. So the progression, this progression signifies the client's anticipate of the server response to make the initial sync communication is done, first initial communication. So in the second handshake phase, with token A, position at S2, the send sync action is triggered, sending token A to S3 and Q2, as you show here in the second figures. So as you can see here, after complete handshake, the colored communication structure, structurally, it has properties such as causality to record all causal events happen during communication. This can assist our understanding of how packets are transmitted between client and server through three-way handshake communication. So it can record all causal events that happen during communication. This can provide administrator and investigator with insight into the causes of DDoS attack and help them to understand how to prevent future attack by understanding their behavior. So the causality features embedded in CSA-Net allows recording the all causality between executed transition, which helps in detecting and tracing the process of such communication. So the investigator now can benefit from extracting all causality of fired transition or moving transition to visually to understand abnormal behavior during this communication and to detect cause and effect of such behavior. In the final handshake step, the client responds via the send acknowledgement action, shifting token A from C3 to C4 and Q3. As you see here in the figure, the servers subsequently receive action, finalize the handshake, ensuring an established connection between both entities. So by receiving acknowledgement from client, the three-way handshake is finished now, and the data can transfer between client and server. This is the end of three-way handshake structurally by using a communication CSAN. However, in the abnormal behavior of sync float attack, attacker manipulates the standard behavior to induce a server, thereby making detection process very challenging. As you can see in the figure, the server fails to receive the third handshake response, specifically acknowledgement from the client, even though the send action is enabled or ready to receive acknowledgement from client. However, token A remains or frozen at C3 and S3, depend on force by attackers. So in the other way, the server will wait acknowledgement from client, and this process make it busy with large number of communication. So this strategy overwhelms the server with a huge number of sync requests, leading to large half-open connection. This is called half-open connection, and consequently making the server unavailable. So we will depend on, as we said, on the features embedded in CSAN to detect all causality happened in the communication in order to understand abnormal behavior could happen. Moreover, reachability analysis is another features embedded in included in CSAN, which is analysis tool or a verification technique used in CSA-Net to determine, for example, whether a specific place can be reached by following a sequence of a step from the initial marking. This can be done automatically in sonograph tools. So this probability is essential for examining the behavior characteristic of any system. Essentially, reachability concern the system's capability to transition from its initial marking to any design state. The figure present the reachability graph for a CSA-Net model illustrate the three-way handshake between client and server, showing that all potential action progressing between client and server. In the classification process, we extend colored communication structure cyclic net by introducing a time color set for each token. So we are enabling it to carry a time value during execution. The color set can be either now timed or untimed, and all places associated with a timed color set are termed timed places, and also the are connected to these places. So the color set of each token now can be described as a vector composed of 6 type details: IP source, IP destination, port source, port destination, TCP flag, and we add now time value assigned to each token. So then we will calculate the time execution for each token inside the model. So the time started from the first execution of three-way handshake inside the model, and calculate the time execution by this equation where tau is the predefined threshold representing the maximum allowable time the server wait to receive ACK from the client. This can be determined by network administrator, and C denotes the time taken by server to process the token, and T signifies the total time of token spent inside the model. So by calculating time for each token, we can classify all normal and abnormal behavior. Here is the classification model for the proposed solution. So to detect abnormal behavior in three-way handshake, we rely on colored communication, a cyclic net based on time value now to evaluate communication between client and the server by time needed to complete the connection. More specifically, time now in CSA-Net is continuously updated during the model execution from the beginning of transition firing. At any given point, we can evaluate the status of each token by inspecting its value. Once the token execution is finished, the value of time represents the duration that the token has spent within or inside the model. For example, in completing time or in completing three-way handshake time. So therefore, we will rely on the time attributes of each token to detect abnormal patterns. In other words, we depend on the predefined threshold to classify token. For example, we classify token as abnormal if their duration exceeds the predetermined time limit determined by network administrator, and don't send acknowledgement to the server, while all packet within this time frame will consider as a normal communication. experiment and result, we utilized the public data set comprising of over 1 million token, each representing a bucket described by by 27 conditional features. These tokens were categorized into two groups, normal and abnormal. So our algorithm's performance was assessed through a confusion matrix, which displayed an impressive or very good accuracy rate of 90%, while 10% error, which could be attributed to other unaddressed TCP flag, because we only addressed in this stage, we only address acknowledgement flag to receive by server. So this is, thank you